Okay, so all right, so the idea right now is very crucial in linear algebra. That's um, where do vector spaces come from? Okay, and so they don't have to be constructed from scratch, but rather they can be found in the spaces that we're already familiar with. Okay, so that's the definition of vector space. Very abstract. So the algebra can be executed uh, within it. And incidentally, we are not doing any geometry right now. And then, and so, but then we have a bunch of Euclidean spaces, obviously. But then you can also know that there is a hierarchy there, and so each lower dimensional space is contained in a high dimensional space, and you can go backwards, including the axes. Okay, all the axes are one-dimensional subspaces, all coordinate axes, and then if you go with that, all the lines. Okay, so that's probably step number one. Seeing subspaces everywhere. Number one is to see the axes. To begin with, they look literally like the line, Euclidean space of dimension one. And so once you have those two in the plane, for example, then you have a bunch of lines too. Any line through the origin also is a subspace. In other words, it's a vector space of its own. So it doesn't matter how it is built, then it is within the algebra, stays within it. Okay, so and then you go to high dimension, say for example, you're looking at three-dimensional space and you still have the axes, okay, three axes, each of which is a copy of a one-dimensional space, so it's everything is happening within it. And then you realize that all these straight lines through the origin, once again, they're subspaces. Okay, then you go on, and then you also go what about the planes? And the planes are the coordinate planes in the three-dimensional space. There are three of them, and then each of which is a subspace of its own. Okay, vector space of its own, and then so there are three of them, and then you just pick any other plane through the origin, and once again it will be a vector space. Okay, so that's how you can just see a bunch of subspaces of all dimensions as you go up in those. But that's not it. So that's an example, by the way, of how you have an n-dimensional space, or in this case, three-dimensional, two-dimensional space, and you drop one of the variables, keep it equal to zero in this case, and you have a subspace. And you can see how it works out when the straight line is through the origin. We speak and we have two vectors on that line. There, the end result is once again is within that line because it's a multiple. It's just a multiple. But if the line does not pass through the origin, getting two vectors that's on the right does not produce a vector once again on that line. Okay, so that's why we limit ourselves to only those that pass through the origin, and that rule applies to all the dimensions higher than just one. So this is just one. And then this is the indirect ways to construct subspaces. So for example, multiple. So this is a multiple. This is the exercise here. A multiple of a vector. So these are multiples of, I take a vector 1, 2, and then multiplied by t. Okay, so that's really in the set. And so what you think about it, you can see that the algebra of vectors is preserved. So you can, if you add two vectors, multiples of 1, 2, the vector is still a multiple of 1, 2. If you multiply a multiple of 1, 1, 2 by a number, then you still have multiple of 1, 2. So that assures that all the axioms, remember the axioms of vector space, right here, too many to remember, will be you can assume as if it is the whole linear algebra is there in that little space, so like this one. Okay, so n-dimensional space, if we fix with the nth component of the vector equal to 0, then once again, when we carry out the algebra, that there is no contribution to that last vector, does not contribute anything. And so the end result, once again, two vectors with zeros at the end will produce a vector with 0 at the end. And so the way we describe it, we say that they are closed under these two operations. So closeness under the operation of addition, and closeness under the operation of constant multiple, if that makes it linear algebra self-contained. There are only two operations to worry about in linear algebra: addition of vectors and constant multiple. So if we have a set within which these operations do not take us out, okay, somewhere else, then we have linear algebra as if everything that we have learned will apply. Okay, including that probably the most important thing here is in this, or the rule of thumb. Okay, the rule of thumb that if you have a vector space, you can manipulate algebraic expression as if they are numbers, as long as the formulas themselves all make sense. Okay, so as long as you add in vectors, you don't add vector to a number, then you're fine. And so once you found these vector spaces for whatever reason, and we will need them, subspaces specifically, then you can do algebra within them, and as if it is just the way you have done it with numbers for so long. Okay, so once again, the lines, they have to pass through the origin. So as I said, it's not one but many, all lines through 0. Okay, so if you go to dimension 2, all planes through 0. Okay, and so on, so on, so on. So that's the whole hierarchy of spaces and subspaces that we end up with here. Okay, so all right, so the next topic is convex, affine, and linear combinations of the vectors. Okay, so once again, we choose building blocks, some vectors as building blocks, and then we hope to construct the rest of the vectors that we care to deal with as the combinations of those. Using that naturally algebra. So that's what this is all about, is the algebra of those two operations. Once again, that's what linear combinations are. So this is where it comes from, taking averages. The idea comes from taking averages. And so, for example, the average of two numbers, you just take add them together, divide by 2. But it's also, as you can see, if you on the right, this one is an alternative way of understanding averages. Is just give it their equal weight, which adds up to 1. So 1/2 and 1/2, and that will be the average. Okay, so that's the average. So once again, as you can see, this is a linear combination. So x and y are combined together, but in a very specific way. So they're given weights, and in this case, they're given equal weights. So that's how we do averages. And then naturally, you do exactly the same thing with vectors. There's no trouble whatsoever to take that formula, and the algebra works out. So you can think of half of a first vector plus half of the second vector. That's supposed to produce in some manner, in some way, in some sense, produce the average of the two vectors. If you plot, you surely will notice that it is the case. Here it is. So the average, I have green and red vectors. Okay, I add them together. Okay, if I add them together, I'll get the blue one. But that's not what we care about. If we take half of it, that's the average. You see the picture on the right. This is the part that has been described, right? So the green vector, the red vector, and the black vector is the average. Okay, so not the blue vector is the sum. So we take the half of it, which so the diagonal in the parallelogram, we cut it in half, and then and that is the average. And as you can see, it kind of makes sense, even though it might be, if you start thinking about, maybe when you want to think about average, and that's something to worry about. You have a vector like this, and you might, well, what's the meaning of the average? And you try to go halfway like this. So angle in half between them. So it would have made sense when, as you can see, that's not the case in what I constructed here. So can you see under what circumstances it would make sense to go half angle between them? So why is it not halfway? You can see the angles do not match here. They have two different angles. Even though it would make sense. You are talking about the average, so the average of vectors are about direction, so y directions is not halfway between them. Why not this? It would make sense, wouldn't it? Well, is the question clear? What's the issue is? It is about the answer is why it's not work out that way, because the length, yes. So the second vector is longer, okay, and that's why it kind of brings the average towards it rather than towards the one that's short. The green one is longer, and so if they were of equal length, think about it, if they were of equal length, then that would the plan that we had, we wouldn't have just a parallelogram. Remember what it's called, this figure called a parallelogram with equal sides. What's called the rhombus. Correctly, I think. And so when the sides are equal, unlike this one, then the angles are equal too. And so our diagonal would go halfway. Okay, if one of the vectors is bigger, longer, then naturally the average would be tended towards it rather than the other with the smaller one. So if you try to build something more extreme like this, okay, so naturally the angle will be very close to the bigger one, and small one, the contribution of the small one will be small in terms of the angle. So in other words, the longer the angle, the more its direction matters. Okay, so the longer the vector, the more its direction matters in comparison to the other. Okay, so the shorter vector does contribute some, but it's because it's being short, its contribution is small. So indeed, it's a parallelogram construction still remains. Okay, so that's the averages. Here's the average in dimension 40. Okay, makes sense. Look at it. So the green vector, the red vector, and then the average between them lies. It's, if you want to think about it, there is some kind of meaningful graph, lies halfway between them, right? Right, so literally we're 2 points at a time, red and green, right about the one below the other, like maybe like this. Okay, so 2 points, and you just take the average. So because what is the vector if not just a bunch of numbers? So one component at a time is average, and then the effect is this. Okay, so the graph, it's not literally the graph, but the values lie halfway every time between the two. Okay, so so yeah, that's the 20th component is literally the average of the 20th components of the two vectors. So weighted average really is what we start talking about if we go beyond just the average when the weights are equal. The combination is alpha x plus beta y, and you are familiar with weighted averages. Anyone? Weighted average like this. We use them all the time. When? What? Grading, yeah, great. So yeah, the different weights to different assignments. So that's in our case in this class, it's the midterms and the final, for example, they give a different weights. So then which means that for you it's not you just add and divide by 2, okay, but rather you pick those weights ahead of time, and the in fact here's syllabus. So where's the numbers? Here they are. These are the weights, and they are expressed in terms of the credit, in terms of the percentages, but nonetheless they are weights. So what are the weights? Right here, the weights are what?
Like 0.1,
0.1, 0.4, 0.5. That's right. So these are the weights. As you can see, they are all add up to 1, right? So 0.1, what is it? 0.1 x plus 0.4 y plus 0.5 Okay, so that's how those are numbers naturally. So, but the idea comes from numbers, and as you can see, it makes perfect sense. If different things weigh differently, so that's how we average them together. But the point is that this is the crucial thing for the whole thing to work out. That the weights end up to one. So they are literally percentages. How much we put on one on the other. So it is about weights literally. That's how if you have weights, you distribute them on the scale, and then they in order for them to balance, you have to put a different weight at the one end. If it is longer, then you need less weight. If it's shorter, you can put less. You need to put more weight there. So it's called the weighted average literally, and then we do it with vectors. Once again, it makes no difference whatsoever. If the algebra works out? Okay, we have created algebra of vectors, and that algebra of vectors in except for obvious things, totally mimics the algebra of numbers, and so whatever we can speak of about numbers, as long as we don't do division and stuff like that, then it applies to vectors. And so if we understand how to do weighted averages with numbers, we know how to do weighted averages with vectors. So once again, it's alpha u plus beta v with alpha and beta adding up to 1, right? So not just that, let's not forget, so they add up to 1, but also they also should be both larger than or equal to 0. Otherwise, it doesn't make sense. And then the average, these are the weighted averages. That's where the weighted averages lie. Okay, the blue ones, depending on how much weight we give. If we give more weight to the red one, we're getting this one. If we're getting more to the green one, we get the other one. And so that's the scope of possibilities, the whole range of possibilities of the vectors, and they all lie on that line. Where does that line comes from? Once again, the parallelogram. Our parallelogram constructed the line that connects the end between them. And the average is there somewhere, right? The average, literal average, 1/2 u plus 1/2 v is among those. So we're expanding from the average, we're moving on to weighted average, which gives us infinite many possibilities. So it is not a rotation though, so we are not trying to think of vectors separately as directions and the magnitudes. That is very not productive. And so when you start thinking about directions, then you want to take the average of the directions. That's not it, right? So we already know that depending on the relative sizes of them, the average will not produce a halfway angle. Okay, so we're dealing with vectors as such. So they're just a direct arrow, so the length doesn't matter. Okay, so once again, this is the averaging in dimension 4. So once again, a gradual transition. So that's an interesting thing to notice. Just like with vectors, it's a gradual transition in a very careful way from red to green, but also with functions. These are sequences naturally, but the gradual transition from one function to another is kind of important. So the question, how do I make, say, sine from cosine, from sine x to cosine x slowly or gradually? How do I transform sine into cosine gradually? Now you know how. Okay, so it's literally you can make a a clip, a video clip, right? So once again, a gradual transformation. You've seen these clips many times, for many years, in fact, transforming one object into another object. So at its simplest is this. Okay, so you have two curves, and how do I transform one to the other? I do this weighted average. I go through all the weighted averages with weight changing from it's say alpha is equal to 0, then alpha is equal to 0.2, alpha is equal to 0.8, and then alpha is equal to 1. Okay, so literally that alpha is time. So that's how you create that clip. You give it, you recompute the thing one alpha at a time, and alpha changes over time in a gradual manner. Okay, so you create maybe in this case you have like what is it, seven frames. Okay, so here I have 7 frames for your video, and then it transforms one graph into the other. And so now once you realize how it's done, you can transform any graph into any other graph. And once you know how to do it with graphs that are curves, now go look at surfaces. Can I transform one surface into the other in a gradual manner? It looks like magic, and then that's once again it's the same story. There's nothing tricky about it. You just do averages, weighted averages, and one will be gradually transformed into the other. Okay. So one phase into the another phase. That's how you could do it. It's more complicated than that, but the basic idea is right there. Okay. So we are making it more and more general from average when the weights are equal to 1/2. Now they don't have to be equal to 1/2, but then there is more to it. We could remove the requirement that alpha and beta have to be positive or non-zero at least. What difference does that make? So did I mention, so the terminology is we're not going to rely on that terminology, but you might encounter. So these are called convex combinations. Okay. Not sure if do we need to justify why it's called a convex combination? Let you think about it. Why it's called a convex combination? And now we are removing the requirement that the weights have to be positive one. So which means that you're not doing it with the say assignments or anything like that. So they could be negative, which means that you can guess what's going to happen. We'll simply pass green and we'll pass red. So more to the left and more to the right. So this is to explain why we can do it. Well, maybe if you would try to balance a scale, then what if one of the forces is actually not the gravity, and so not pulling down, but pulling because of the spring, it's pulling up. Okay, so once again, so it makes sense to give a negative weight to an object. Okay, because it's being pulled in the opposite direction. So that's an explanation of the whole thing. And as I said, the end result is there's still the ends of the vectors lie on the same straight line, but now they can progress to the left and to the right beyond green and red. So like this. Yeah. So in between when both of the weights are between 0 and 1, they lie between those vectors between the two. These are the convex combinations right here. Okay. So what if there are no restrictions on the weights or at all? So in other words, the restriction that I'm keeping is here, and I forgot to mention alpha plus beta is still equal to 1. So it is a balanced weight. So we can still speak of weights even though they are not really any more literal weights. So then we call it a linear combination, and we've had it literally in that problem. Remember the problem about coffee on the first day of classes. It is a combination of the two blends, of two coffees to create the blend, and then it doesn't matter. It's entirely up to us to put any number of any weight can be assigned to the Kenyan coffee and to the Colombian coffee. So they do not have to add up to 1 necessarily. They actually add up to 6. Right, so the total weight is supposed to be equal to 6. Once again, we're speaking of x and y's weights, and they're literally weights. In this case, they cannot be negative, but at least they surely could be any numbers. So it doesn't have to be between 0 and 1, nor do they have to add up to 1. So in fact, the second requirement is what it creates. Creates the whole problem. Okay, so the geometric meaning then we saw it. Okay, so this is the solution, right? So that's the first look we took at it looked like this, so the solution, but that's not really the way we are interested. We've been addressing it. We address through we will see in a minute a linear combination in a more precise way, but let me still make my point that this is a linear combination of numbers. Meaning of 2 and 3. 2 and 3, they are prices of the two types of coffee, and then if you're creating a blend of that with a weight of x for the first one, y for the second one, then you create what we call, the language once again is still to be explained, a linear combination of the two. So no restriction whatsoever in the second formula on x and y. So linear combination of 2 and 3. So it's a numerical linear combination now of numbers. Okay, so now what about vectors? And once again, we will see how that emerges. How linear combination emerges. We had a little bit of that, or I think we'll just look at it one more time. So okay, let's rewrite the whole thing here in terms of why we've been building linear algebra, vector algebra specifically, so we can rewrite these word problems about mixtures into the language of algebra. Okay, so in other words, that the system of equations that we have, we can break it down into vector algebra, and that's what it is. In fact, so as you can see, that this is my first step here is to realize that two equations, two equal signs, I convert it into one. Okay, so these two converted into one. That's step number one. So in the left-hand sides of the two equations are combined together into one vector. In the right-hand side are also combined into one vector. And then what does it mean? In fact, I could go both ways here. What does it mean for two vectors equal to each other? That literally means that the first components are equal and the second components are equal. Okay, so that's what's written on the left, or it's on the right. It's exactly the same thing. So it was entirely our choice to choose what's on the left or on the right. We're using the algebra that we already know, and so it's called the coming out decomposition. As you can see now, I'm doing the same thing with addition. So addition within the two separately, separate addition within the two components of the vector can be replaced with one single addition of the two vectors. So what does it mean to add two vectors? You add their components, component y. The first component x plus y, second component is 2x plus 3y. Okay, so that's literally what addition is. And that's except we're moving in the opposite direction. So literally, usually we go what's on the right, and then we how do we add two vectors? That's how. But we are decomposing. In other words, we have already everything sort of kind of computed already, and we want to represent it in the form of vector algebra. Okay, so now you can guess what's next. What's next? In the language, so I used what vector algebra is made of is actually three parts. Things being equal, and we do addition. And what's the second operation on vectors? A plus b, and what's the operation on vectors? Addition and the other operation on vectors. Scalar multiplication, yes. So say k. Okay, so and so this is what we have been working so hard on to actually have the algebra of vectors as if with the same symbolism as in the algebra of numbers, and with the same rules, and then so we want to use it, and so I use the equal sign right there, number one. So if I were to mark it number one, number two, number three. So I did number one, I did number two, and now I'm doing number three. Okay, what do I do with it? That expression on the right. How do I apply number three here? See? Moving backwards. Where is this? Where is the scalar multiplication here? See? So whatever is repeated twice can be now on the left. We have done it already twice. Whatever we have done twice on the left, it is done once on the right. So that's the component-wise equal and component-wise addition is converted on the right into vector equality and vector addition. So now we take this and convert something into scalar multiplication. So do you see repetitiveness on the right here? There is a repetitiveness right there staring at you. You see? X appears twice. And Y appears twice too, but to begin with, X appears twice. So what does that mean? How can we use it? That's what scalar multiplication is for. How do we multiply a vector by a scalar? We multiply each component by that. Okay, so if X is present twice, it means that I can factor it out. Okay, like this. Okay. It is X multiplied by 1, 2. So here X is present twice. Okay, right here. So I just factor it out. And Y is present twice, I factor it out. So that's scalar multiplication once again. So that's that stage 3 of our conversion, converting numbers. So multiple numbers converted to single vectors. Okay, so multiple meaning, well, pairs of numbers. Pairs of numbers are converted to, each of them is converted to a single vector, and we did it multiple times. And I need to look at it. So X times 1, 2, what does it mean? It means that the, well, I'm probably, let me correct myself here. That's what I mean here, 1 plus. Okay, so this is how we progress, like this, yeah. Okay, so, okay, so then each of these two vectors, x to x, is now converted into x multiplied by 1, 2. And y, 3y vectors converted to y multiplied by 1, 3. Okay, and we recognize this as what? As what? Two vectors with coefficients added together. What do we call it? I've been calling it today. Two vectors, 1, 2, and 1, 3. When I multiply 1, 2 by x, what do I get? What's the meaning of that? What's the meaning of scalar multiplication? What does scale multiplication do to a vector? One, 2 multiplied by x, what happens to the vector? This and that. So what are these? 1, 2 multiplied by x. If a vector multiplied by 2, what does it do to the vector? Doubles in length, right? But direction is the same. So that's what the multiple is. It's literally stretches or shrinks without changing the direction. Okay, so that's what happened. So we took 1, 2, and 1, 3, multiplied them by stretched them in the directions, whatever, but we don't know what x and y are yet. And then added them together. That's once again a linear combination. A linear combination. Let's visualize it. Okay, so it's supposed to equal to 614, by the way. So look at it. So these 3 operations combined together, a linear combination of 1, 2, and 1, 3 with unknown coefficients supposed to produce 614. So finding those x and y is actually what does it do? It stretches these two vectors, and the result is supposed to be 614. So this is, yeah. So that's the problem now rephrased. The original problem right here on the left. So find x and y, so that x plus y is equal to 6, and 2x plus 3y is equal to 14. We rephrased it. So that's the original right here. And now we are the original, and then this is new. A vector equation. Rather than having 2 scalar equations, a numerical equation, now we have one vector equation, but the answer is still the same. So find x and y. Okay, so find x and y. satisfying this or satisfying that. It's really not, doesn't look like a lot. The top and bottom, if you compare it does not mean a lot to us as in terms of it doesn't simplify things. But we're not trying to simplify things. If anything, we're trying to make them things more complicated. So why do we make things complicated? Why do we make things more complicated? It might look complicated. So we introduce a new concept. We introduce vectors, and the problem is has become more complicated. So why do we want it? Why do we want anything more complicated? More complicated. Anyway, so the point is that then we for one a lot of benefits, as a matter of fact. But one is that we will be able to visualize. Okay, so visualize the data. Okay, so once again, this is what we're looking for. U is a vector 1, 2, V is a vector 1, 3, and that we're looking for just a perfect linear combination, where you can think about putting different weights on x and y, literally, so that the end result will be 614. Okay, so in other words, what we're not allowing let's just put it here. We're not allowing negative weights because it doesn't make sense in this context. But generally, we speak of linear combination of U and V supposed to produce 614. So it is a kind of backwards problem, once again, inverse problem. So the output is known, and we want to find the inputs, x and y being the inputs. But that the geometry itself is once again, it's about stretching. And so this is what I'm talking about. So on the left here, this is the setup. So I have a vector 1, 1, 1, 2, and 1, 3. And now what I'm supposed to do with them, I'm supposed to combine them in just the perfect way, so it would produce 614 over there. Okay, you can see if you trial and error here, if I add the two vectors 1, 2, and 1, 3, you can tell that it's actually not, it's not going in the right direction. So we realize that the weights cannot be equal to each other. And so this is 2, 1, 2 plus 2, 1, 3. Once again, they're equal weights. And so once again, they're not producing the right result. So trial and error, literally, you can carry out with a trial and error, and the 4 weights for the first vector and 2 for the second does produce 614. Okay, so just trial and error, moving them up and down a little bit. And it turns out that to get the right direction, actually the second one, the first one rather, has to have twice the weight of the second. Okay, so that's this problem is solved. So 614 has been produced as a linear, it has been recreated as a linear combination of the original vectors 1, 2, and 1, 3. So that's a linear combination problem, and that is the new interpretation of our problem, of the problem that we started on the first day of class. Remember, so we're not speaking, and we solved the problem by 2 lines that intersecting, but this is better. So that idea certainly goes into high dimensions, and that's the second benefit. Visualization is not going to be as easy anymore, but nonetheless, if you sort of acquire this understanding and field for vectors as algebraic entities, so you can do algebra with them, you can carry it on into high dimensions. And so the story would be the same if you had a mixture of 3. Imagine 3 vectors, so it's a mixture of vectors, if you like, even though this was about coffees. But once again, you have 3 vectors, and you have a fourth, and you need to combine these 3 vectors in such a way to produce the fourth. That's a typical mixture problem now. Mixture vectors. That's what a combination stands for. Okay, so all right. So multiple fails, and then we just somehow we got to went through all the linear combinations, found the one that is the correct. The only one is correct, as a matter of fact. So it's not entirely clear why. So that's an exercise. Only one. There's only one correct combination. So okay, so we're not speaking of points anymore, x and y's or vectors, but we speak of directions. Okay, so that's these are the directions. If you start doing linear combinations of two vectors, that's what the end result is. Literally infinitely many a whole array of vectors that you can create from two, depending on the weights that you pick. In the middle is you zeros, and then you have one pointing in the single direction, and then you start doing them in all possible directions. That's the effect. So any two vectors can be picked. In this case, I pick 2, 1, and negative 1, 1. And as you can see, if I go through all the linear combination, what's the end result? I'm covering the whole plane. Okay, that's the whole plane. We have had that already. So linear combinations of these, of U and B, okay, produce the whole plane. When did we recently have a very similar situation? Linear combinations of two vectors produce the whole plane. What's the easiest choice of those two vectors? Linear combinations of two vectors taken together cover the whole plane. Okay, that's the picture that you're looking at. What other vectors we picked many times with the same effect? What's the easiest choice? Linear combinations of two vectors that will cover the whole plane. Don't recall a situation? No? Just like I remember I and J, 1, 0, and 0, 1. That's the simplest choice. So I choose vectors like this. And then once again, that's the basic. These are it's called the standard basis, remember? And then once again, every vector can be decomposed into a linear combination of these two vectors. And then now, as you can see, it doesn't have to be necessarily these basic vectors. So remember this: AB is equal to AI plus BJ. Yeah. Okay, so all right, so that's the good news, and so they just in case these are the formal definitions. Linear combination, going backwards. Linear combination is any sum of two multiples of two vectors of the two vectors. Alpha u plus beta v. So that applies to with no restrictions on alpha and beta. That's a linear combination. So that's why it's the most important one, more important one, as it is linear algebra. And then if you put the restrictions on these numbers, such as you require them to add up to 1, that's called an affine combination, and a convex combination is also, in addition to, you require the alpha and beta to be larger than or equal to 0. So in other words, weighted average. That's what the last one. Okay, so these are the how we can visualize two vectors. So once again, we already had it. Convex combination lies between the 2 points. The affine combination gives you the line, but now what a linear combination gives you the plane. Okay, so that's you can see the difference in terms of the dimensionality. Linear combination is way bigger. Because why? Because what is that restriction? Alpha plus beta is equal to 1. It's a 1 degree of freedom taken away. Alpha and beta, 2 degrees of freedom. If you impose a restriction, a relation between alpha and beta, then you have only 1 degree of freedom. So you have fewer dimensions. After all, you can have alpha u plus 1 minus alpha b. Okay, so it's a single degree of freedom, and so it's a line. Okay. Okay, so this is once again from two functions. What can you build from two functions? These are 9 linear combinations of the two functions are on the left, u and v. Once again, you can think of them as the same. It's just like 40-dimensional vectors. And when you start doing linear combinations, these are the vectors you get. Once again, in dimension 40 rather, as you can see. So all variety of functions. One from naturally u and b re-emerge here as functions as extreme cases. Then there is an average between them somewhere, which it is 1 and 1. Okay, where's my average? Uh, uh, 1 and 1. This is the average. This is the average. Okay, so of u and b. Okay. This one. This is, hold on a second. Where's my here? No, the 0. Okay. 0 and 0, and then the average is 1. The average is 1 and 1, and then there's a this is u. Oh, hold on a second. Okay. This is u, and this is b. Yeah, and this is b. So all linear combinations. So it includes the average, the plain average, including the u and b themselves, the real ones, and then the 0, and then the rest of it. You can see it's a whole table, and they all have 9. But you can imagine that all the numbers between 0 and 1. That you can continue on, insert as many numbers as you like here, and beyond to the right or to the left. So it's a whole plane filled with graphs of functions, and you can build them from just 2. Okay, so now that's the crucial step, and the more challenging is linear combinations of multiple vectors. Okay, so this is when you have 2, you have a table. When you have 3, when you have 2, you have a table of graphs. When you have 3, what do you get? 3 weights. So what does it look like? Yeah, so if I were to add another one here, say W. And I want to do the averages once again. Linear combination, there is really no challenge here. Alpha U plus beta V plus gamma W. Okay, a linear combination. So once again, there is no restriction on alpha, beta, gamma. Just any 3 real numbers. So can you imagine how you would visualize all the linear combinations? Instead of a table, what would we get? Is this the picture itself? Is the picture itself the table? Is it clear? So this is yeah, to be clear, this is alpha. Over here, alpha runs between 0 and 1, and then on and on with all the rest of the values. So just skipping some, and these are betas. These are beta. Beta. This is beta. Okay, and this is alpha. So change in the horizontal direction gives you change of alpha, which means that it contributes to the weight of u. Okay, from this is, by the way, this is negative u right here. If this is u here, this is negative u, right? Upside down. If this is v, this is upside down. This is negative v right here. Okay, so okay, so once again, alpha reflects the contribution of u. Beta reflects contribution of v. How do we also add the contribution of w? Well, we need the third dimension, right? So the alpha, beta, gamma. Okay, so this is actually the table is here is as if gamma is equal to 0, and so there is no change in terms of gamma. If we were to change gamma, then we would have progress in the third dimension. So it would be, instead of having a table of graphs, we would have like a box of graphs. So and now, so you can see how things become complicated. How as we go to high and high dimensions. So in this case, we are, even though the graphs themselves already are 40 dimensional, but that's not really the issue. The issue of difficulty is how many we've got, and then it doesn't matter how many we've got. We can making linear combinations of them make sense. So examples, once again, you can think about making, rather than making a mixture of, say, two types of coffee, you have three types of coffee. Or you have, if you want to think about portfolios, then you might have a few thousand stocks and bonds in it and available. Okay, and then you want to decide to create your portfolio. You can decide how much of each you want to have. So available stocks, bonds, and this is how much, how many of each that we choose, and this is the total value. Okay, so available stocks, bonds, meaning the prices. Okay, so hold on a second. Well, you could. This is oversimplified situation when if you start with stocks and bonds, each of them probably is the basis. Okay, so this is a one, a two, a three. So these are the choices, the basic choices. Okay, so then which we already have talked about, and so you can choose your portfolio by picking how much of each of those three or 1,000 you want to have. So that's the initial point of view on linear combinations, and especially on bases. So this is the standard basis, and actually, if you talked about mixture of, then the basic choices are given to you already. Okay, so that's what we have. Now we are beyond that. Okay, so now what we're doing here is each of these vectors is not necessarily one of the basis things. Okay, they are already themselves. These are combinations of the variable stocks, right? So imagine that once again here we had only two stocks and bonds. Okay, so like this. One is so this is two-dimensional. Okay, so you can certainly think in terms of coffees, and then number one is once again Kenyan coffee, right? And the second one is Colombian coffee. Okay, so then one, two, what is two, one? It is you have 2 pounds of Kenyan coffee and 2 pounds of and 1 pound of Colombian coffee, and then you have negative. Okay, negative one maybe that doesn't work out quite well, but so let's drop this negative one here. One and one, and that's mean 1 pound of one and 1 pound of the other. But then you're doing linear combinations. What's the effect of it is? It means that you are taking two mixtures and mix them together. Okay, so in particular, you can go with 3 and 2, for example. If you add these two together, you have a new mixture, which is now 3, 2, and you can reinterpret in terms of the original choices. But nonetheless, it is a linear combination of the blends. Okay, so these are the blends. But once you have those blends, you can do algebra with them, and so you can recombine them. So by some circumstances, you are not in the position to buy the stocks and bonds, but rather you are, let's say, blends, and some blends are being delivered to you. You know, however, what they're made of, and so you can smartly combine them in such a way that receive almost any combination of the two ingredients would be available. Okay, so for example, if I have these two blends, 2, 1 and 1, 1, have been delivered to me, then I could produce 3, 2. I could put more weight. If I want more Kenyan coffee, I put and once again, I do not have access to Kenyan coffee nor Colombian coffee separately. I will only have access to these blends. So then these blends are now to be combined to produce more one or the other as much as possible. Unfortunately, because both of them contain Kenyan coffee, I cannot, for example, get rid of the Kenyan coffee. So that's an impossibility problem. So, for example, so if this is U and this is V, okay, so you might require U plus V equal to, say, 0, 1, and this is impossible because each of them contains some of the Kenyan coffee, so I cannot have 0 there. Otherwise, just about any other combination is available, and so I could put more weight on the. I could reduce the amount of Well, actually, by the combination, it seems that you always have more Colombian coffee than you have Kenyan coffee, unless you're allowed to have negative weights. But that's physically impossible. Okay, so that's the analogy with coffee. And now if you go to do analogy with stocks and bonds, so then you are combining portfolios. Think about it. So U is a portfolio and V is a portfolio. Okay, so they made up some option, some original stocks and bonds, and now you're combining these. You once again, for some reason, you don't have access to the original instruments, so you create these synthetic instruments and combine them together into new ones. And so Unity V1, VM are actually those combinations, the portfolios, right? And then you can combine them together. And you can accomplish hypothetically, if we only had the ability to have negative numbers here, you can combine, also produce any original stocks and original bonds if you want. If you're able to subtract, then that is guaranteed. So that's analogy. Probably the mixture analogy is the best. So if we originally spoke of some original choices and their combinations, okay, so that's nothing literally the components of the vectors. Now what we speak of is mixtures of mixtures. Okay, so yeah. Okay, so like I said, V1, VM might themselves be, they're entirely arbitrary, and so we can combine together, and you can have as many as you like, and then the linear combination makes sense. Okay. So all right, so that's what the most important really thing about linear algebra. So the rule about linear combinations is that if you start with the basis vectors, remember the basis vectors E1, En. Okay, so when all the coordinates are equal to 1, these are the original choices, and then every vector can be represented as linear combination of those basis vectors. So, all right. So, is it always the case? The question is it always the case? So, it works out with the basis vectors. So, every vector can be decomposed into a linear combination of the basis vectors. What if we choose, as with the whole point here, was what if we choose vectors that are not basis vectors? And so, what can go wrong in that respect? And the example is probably here. So as you can see here, we have both the original vectors, the original basis vectors, and every vector right here can be decomposed into a linear combination of I and j. Then it works out for u and v as well, as the picture suggests. So so the question really is how can it fail? How can it fail? Is it possible to have two vectors that all of their linear combinations will not produce the whole plane?
You have 0, 0 vectors?
Well, that's not the answer, but I was looking for, but it is the surely is would be a vector. Say u is equal to 2, 1 as before, but now what if b is equal to 0? Okay, so why is it not working out?
You have nothing to scale by but 0.
Well, yeah, but can you point out the vector that's not there? I take all the linear combination of these two vectors. You were saying that we're not going to get everything. So which can you point out the vector that's not there?
Well, we have two sets of empty vectors. Could you make anything out of them?
Well, I think the more extreme example that you're suggesting is 2 zeros.
Yeah.
Okay, so well, that clearly, when you do a linear combination, you have nothing but a 0. So that's surely the number one example of how it can fail. Now, less extreme that I thought you were suggesting is u is equal to still to 1. What if one of these vectors is 0 and the one is not? I say it still fails to get the whole plane. So all I have to do to demonstrate that it is the case is to point out the vector not covered. Can you think of a vector not covered? So I'm speaking of alpha 2, 1 plus beta 0. Okay. Can you think of a vector that's not there? No matter what alpha and beta pick. Let me help you out. 2 alpha, well, probably easier to think alpha 2, 1. Beta does not contribute at all. Okay, so it's literally the best we can produce from these two vectors is alpha multiplied by 2, 1. In other words, these are all multiples of u. Okay, so you see the problem, right? Right. In any other direction other than 2, 1, we fail to get it. So give me one. -37, okay. Why not? -37 is not a multiple of 2, 1. So it's out. Okay, so we have two vectors and it did work out. Even less extreme example, u is equal to 2, 1. How about v is equal to, anybody can suggest v is not equal to 0, that would have the same effect. No, 1, 1 is fine.
That was the same vector.
What if it's the same vector? Okay, so when you have two vectors, what do you get? So can you give me a vector that's not covered?
3 wouldn't be covered.
3, 1, 3, 1, sure, yeah, so as long as it's not a multiple, it's not covered. Okay, so what if I put 3 here? So the vectors are not equal to each other, but they are parallel. When we start doing linear combinations, the end result is still the same. It's still the same. So the redundancy is the problem. So when the vectors are multiples of each other, they don't create this second dimension. There's no way to get into the second dimension. You cannot cover the whole plane. So that's the problem. And so in other words, it will work out every time. So how can it fail when the two are the answer? One answer is when they are multiples. Once again, redundancy it becomes redundant. When they are multiples, they are redundant, and then therefore they are not unable to cover the whole plane because there is no enough degrees of freedom. There's still 1 degree of freedom left. Okay, so that's the big idea, and it turns out that that's the only restriction. So if they are not multiples to each other, they look like this, you're covered. Okay, so this is bad, this is good. It's very simple. The idea goes to higher dimensions the same way is their redundancy. So when we have 3, think about the same idea with 3 vectors. So that's not as easy. So between the 3-dimensional space, and you can guess that we got to need 3 vectors. Okay, so which ones? And so you can imagine that 3 vectors looking like this are okay. But if they're multiples of each other, it's not okay because once again, it's you have only one straight line. Unfortunately, this is also a problem. You see what
if they're all on like the same
on
plane.
the same plane, right? So if you start doing algebra within the plane, you're not going to get everything. You'll stay within the plane. So that's once again the redundancy is a killer as far as the having covered everything. So entirely the whole idea is expressed in terms of linear combination. So is the third. So why is this bad? Like this, because a third is a linear combination of the first two. Okay, so that's the redundancy, and so that's why it not works out. And every time you get a vector, it has to go in the other dimension. So we'll look into that right now. This is just illustrating the combinations to work out this idea that if we have basis vectors, the ones that are actually in some sense they're perpendicular, even though we don't speak of angles here, We're not doing geometry right now, but nonetheless, it is the basis vectors. Then it works out perfectly well. And look at the number. Look at the number. So that's the number of vectors matches the dimension of the space. Okay, so if it is less than or more than, we will have one or the other problem. So one problem is that we don't have enough vectors, and on the other end, we have too many, which means that you might represent the vector as only a combination, but more than one way. Okay. So this is an example, maybe bringing us back to calculus pre-calculus, is what a polynomial is. A polynomial is a linear combination of powers. Okay, look at the formula, right? Their powers, starting from 0 up to n, and then what we give each of them a number and add them together. So that's literally a linear combination. And then we naturally, what that means? It means that indeed all the polynomials are actually it's like an n plus one dimensional space. It's not really such a big space, turns out. Okay, so because every it literally you can write it like this: a naught, a1, an. So an coefficients of a polynomial correspond to a point in the n plus one dimensional space, and therefore all polynomials are taken care of if as long as we stay within that space. Okay, so that turns out to be a very. It turns out that if you would stick to polynomials only, you are actually within the reach of linear algebra. You're not doing anything. So you can actually do differentiation and integration with no knowledge of calculus. So if you might remember, as a matter of fact, if you your calculus textbook, it says calculus and the early transcendentals. The transcendentals are anything beyond polynomials, roughly speaking. Okay, and so if we do not do early transcendentals, you do this. You do calculus with nothing but polynomials. And once again, so for example, let me give you an example. So I'll give you an example of differentiation. So as we know, I have, say, what a naught plus a1x plus a2x squared. Okay, if I differentiate, what do I get? I get 0 plus a1 plus 2a2x. Okay, I remember differentiation. Okay, so I could do it in terms of vectors. So the vector a naught, a1, a2, under differentiation, it gives me, you see what? The once again, the vector comes from as a linear combination of powers. So a0, the first entry is what corresponds to the 0 power, and the second what corresponds to the first power, and the third to the second power. Okay, so as we read this, what do we see? We see that what corresponds to 0th power? No, 0 is 0, so it's just 0. A1 is what corresponds to the 0th power. A1, 2, A2, and then this is where 0 is. So that's the whole differentiation for you. So that's the calculus of polynomials is pretty much nothing but linear algebra. Okay, so I'll stop here and see you next time.